The next question is January 2006 AS2, and this question is question 1. Again, it's a question 1 from module 2, or the old module 2, which was called Waves and Photons. A travelling wave is propagated through a medium, disturbing the particles of the medium as it passes through. So a travelling wave is a wave which transports energy, and therefore that could be either a transverse wave or longitudinal wave. Although the wave transports energy through the medium, it does not carry the particles of the medium along with it. So that's your definition of a wave. Describe the motion that they undergo. Now, all they're looking for in their answer is that the particles vibrate as the energy passes by. You don't even have to say specifically how the particles vibrate, because in the next part of the question, it says, state how the motion of the particles relative to the direction of propagation distinguishes between a transverse wave and a longitudinal wave. I'll just scan in a wee bit there, if I can. This way. That's just your definitions, if you know your definitions. So a transverse wave, the particles vibrate in a direction which is perpendicular to the direction of propagation. And then in a longitudinal wave, then the particles vibrate parallel to the direction of propagation. Propagation means what direction the wave is moving in. Okay, so that's a very simple 3 marks you could have got there in describing how the particles move. The next part of the question, and I'll scan out a wee bit so you can see the whole thing. 2 types of waves generated by earthquakes are primary waves, which are longitudinal, and secondary waves, and they're called S waves, which are transverse. Both come from the centre of the earthquake at the same instant as the earthquake starts. The speeds of the waves depends on the type of earth and rock through which they pass. Figure 1.1 is a graph of the way in which the distance x travelled by an S wave in a certain earthquake-prone locality depends on time t. The average speed of the p waves, so this is the S waves, the average speed of the p waves in the earthquake in this locality is 550 kilometres per minute. On figure 1.1, which is that graph, draw to scale a graph of the distance x travelled by the p wave against time. Label your graph p wave. So you know that the average speed is 550 kilometres per minute. So we need to work out a few distances for each of these times. So if you know that speed is distance over time, then distance must be speed by time. And so the distance is travelled at time 1 minute. The distance is just 550 times 1, which is 550 kilometres. At 2 minutes, the distance is going to be 550 times 2, which is 1100. And that's enough to get you your graph, but we'll just do 3 minutes as well. And at 3 minutes, then the distance is 550 times 3, which is 1650 kilometres. Okay, so we're just going to put those onto the graph. And so the first one is 1, corresponds 1, 550, and 550 is there. The second one is 2, 1100, 1100 is there. And the third one is 3, 1650, and 1650 is there. And we're going to draw a straight line through those, which should also go through the origin, roughly. And label it P. Now they may not give you the marks if you don't label it P. And there's your graph. So the next part of the question, when you have answered your completed your answer to B part 1. The P and S plots in figure 1.1 should look like those in the sketch in figure 1.2, which is this graph here, and it's not to scale. State what the length of a line MN now shown on figure 1.2 represents. Now it's the length of the line, and the length of the line here is obviously a time. If you look down there, that's that length. It corresponds to the x-axis, and it's obviously a time. So it's a time between. So this means they've travelled the same distance, but this is a difference in time. So it's the time between the arrival of the P and S waves at a certain place or at a certain distance. After an earthquake in this locality, signals received at an observing station are analysed. They show that the S wave was received 1 minute after the P wave. Use figure 1.1, which is your original graph, to deduce the distance of the centre of the earthquake from the observing station. And so we need to get a distance. And if we look back at this graph again, what we need is a difference between these two lines across this way, the way it was shown in the diagram in 1.2, which gives you a time difference of 1 minute. That's what you need. And so if you put this down, we're looking for a time difference of 1 minute, which is 2 centimetres there. So if we put this down and slide the ruler up until we come to roughly 2 centimetres, and we're coming close to it about there. I think about there is probably the right place there, so we'll just draw a line across there. And what distance is that? That distance corresponds to roughly, there's 750, 850, about 900 kilometres. Across here, it corresponds to about 900 kilometres. So the distance here is 900 kilometres. On figure 1.3, which is this graph or this diagram down beneath, sketch where the centre of the earthquake could lie in relation to the position O of the observing station. Now we know that it is 900 kilometres away, but we don't know which direction it's in. So it could be out here, it could be out here, it could be out here, it could be anywhere around in a circle here. And so all you have to draw there is a circle right round. And you know that the radius of that circle is 900 kilometres. And we'll maybe just put that in there. That's the radius of your circle. So that signal that's received at O could have come from anywhere around there.